So, welcome back to our seminar. So we're very pleased to have Julio Hoffimann here today. Obrigado. So Julio Hoffimann, our speaker today, is a postdoc at IMPA in applied math. Previously, he obtained engineering degrees from the Federal University in Pernambuco and then a PhD from Stanford in geostatistics. He was also at IBM Research here in Rio de Janeiro for a couple of years. And today he's going to be telling us about a project that he did with Vale, which, as most of you should know, is a very important Brazilian mining company. And he'll be, well, giving us some insights and some information about how that went, right, how that project went. So, please.
Thank you, Roberto, and welcome everyone to our Centro seminars. So today, as Roberto mentioned, I would like to share some interesting work that we did in partnership with Vale. And so the results that you see here today are just the beginning of a long-term research collaboration with Vale to advance the application of mathematics in the mining industry. So I've created this link on pigeonhole.at/132465 if you want to ask questions or vote for questions from other people in the audience. And at the end of the presentation, I may try to address some of the most voted questions. So feel free to ask as many questions as you like in English or in Portuguese, and feel free to vote in the questions that you feel are most interesting to be answered live. So now that we had set the stage on how we'll be handling questions at the end of the presentation, let me start by acknowledging the people who participated in this project, right? So this project was coordinated by myself and by senior geologist and specialist and colleague Elizabeth Fonseca at Vale. And the list of people included students at IMPA who helped with the research, development, and hands-on programming of the final solution, José Augusto, Lucas Rezende, Marlon Matias, professors at mining engineering departments, my colleague, Professor Douglas Mazinghai, and a senior team at Vale who made this project possible by creating an amazing data set and by providing support and direction whenever we needed. So, in order to understand the problems that we'll be addressing here, we need to get a basic notion of geometallurgical modeling. So geometallurgy is this practice of combining geological knowledge, geostatistics, which is the branch of statistics developed for geospatial data, and extractive metallurgy for the creation of geospatial predictive models. These models, they are used to optimize industrial processes at the mineral processing plants. Like my colleague, Professor Douglas Mazinghai likes to say, it's a systemic view that considers a very diverse type of geospatial variables in the mining industry with interesting mathematical properties, as you will see. So in a sense, like this geospatial model that we're talking about is for any location of this mine, any x, y, z coordinate, we want to predict a set of variables. We'll discuss what these variables are in a minute. So, in a nutshell, a mining company such as Vale wants to create these geospatial models for planning their activities, right? So, in the first step, they create these predictions of ore grades, comminution indices, and metallurgical recovery, which are the variables that we'll be discussing here. And these geospatial models, as you see here, are just 3D grid models, where each of these blocks has assigned to it some values, right? The idea of creating these geospatial models is in order to plan where to extract the next blocks with material, and how to blend these blocks into a pile of material that has desired properties, right? So you have this block model here, which is a set of geospatial predictions that you can decide where to collect and how to mix them together into what's called the blend. This blended material then enters into the mineral processing plant, which is this illustration here at the bottom. And this mineral processing plant is made of several stages that we'll be grouping here into grinding stages and flotation stages. The grinding stages take this these piles of material and break them down into smaller and smaller pieces. They make it finer and finer. And this processes usually consume a great amount of energy. Think of city-scale energy consumption. When this material is fine enough, it enters into a sequence of flotation stages. These flotation stages are fluid dynamic processes that split material that has economic value. So material that has economic value floats, and the material that doesn't have economic value goes down. It's called the gangue material waste. So with this research collaboration with IMPA, Vale is leading an initiative to minimize the energy consumption and waste in their mineral processing plants. It's clear that in order to achieve this goal, it's useful to have better and better geospatial predictions of the mine, because that's a sequence of activities that start at these predictions, right? So we need to have better predictions of these variables. As you see, there are three kinds of variables that we'll cover here.
I think Professor Schultz has a question.
Actually, once more, before I worked in this field, I didn't know what is OR, so I hope. So maybe it should be defined. So the thing is, does it, is it always the bad thing which is floating and because for instance, okay, gold is much heavier than almost everything else.
Yes.
So would it float, would again the float?
May I postpone your question to the end, Charles, because there are so many slides that I can ask at the end with everything, but the idea here is that we deal with a mineral deposit of copper, basically, so we can go into more details later, and maybe I can refer to your question to the deposit, the mining team that worked more closely with this, okay? Because there are many slides to cover. So these three variables that we're going to enter in more details now, so maybe I can actually answer your question partially, are ore grades, which is how much of the mineral you have in each of these blocks, comminution indices, which measure how competent this rock is, and metallurgical recovery, which measure how much you can recover from this rock sample, right? So let's go first with the ore grades. So ore grades, what's the ore grade? Ore grade is nothing more, for example, for the ore grade of copper, is nothing more than the mass of copper divided by the total mass of the blend, right? So suppose you have a rock sample here with a given volume, VA, and density rho A. This number here, X copper of A, is the ore grade of copper in the sample A. Similarly, we have another rock sample B, which has a volume VB, density rho B, and ore grade of copper. The question that we are interested in, say that we mix or blend these two rock samples into a new rock sample here with volume V total. The question is, what's the ore grade of the blend, right? So here's an interesting property about ore grades, right? So if you want to just use the definition, the ore grade of copper is the mass of copper in A plus the mass of copper in B divided by the total mass. And if you assume that, say, the density is near constant or approximately a fixed value, you can represent the ore grade of the blend as a volume-weighted combination of the ore grades of the constituent grades, right? And that's an interesting property that we'll be saving in our minds, right? So the answer is the ore grade of the blend is a volume-weighted combination of the constituent grades, right? So if you actually fix the volume of the input, so you say that the volume of A plus the volume of V is fixed, you can even say that this weighted combination is actually a linear combination of VA and VB, right? So you're saying, if I want to predict what's the ore grade of the blend, I can just take a volume-weighted, say, or linear combination of the volumes, because this denominator here is fixed, let's say. Going even further, if I just make these volumes equal, so if I say the sample A and the sample B have the same volume, I reduce this to arithmetic averages, right? So in the mining industry, these variables are called additive. This is the jargon to say that we can take arithmetic averages as good estimators of ore grades, right? The second important observation is that we saw that these weights, let's say, in the case of ore grades, are linear functions of these volumes. And they are arithmetic averages because we just saw this simple algebraic manipulation, right? But there's a very high geospatial uncertainty. What the mining industry does is it drills these holes, a bunch of them, a couple hundreds of these holes, but there's still a very large amount of uncertainty in between the drill holes. When the arithmetic averages are good estimators and you have linear functions of the volumes and coordinates, we can go to the traditional data-driven approach of geostatistics, which is usually Gaussian process modeling. And you can just use Kriging estimation, Gaussian simulation to interpolate these drill holes and fill in the gaps between the drill holes. And that's basically a literature that goes back to the 50s, 60s. It's super old, right? Now, what's the challenge with geometallurgical variables, right? So geometallurgical variables, they're not additive in the sense that we have just described, right? If you take, for example, the hardness of minerals in this Mohs scale here, if I take talc, fluorite, and diamond, and if you put them into a scale of hardness here, which is actually an absolute scale with this sclerometer, you see that they don't have linear behavior, right? So the hardness is increasing here without some weighted average combination of the samples, for example. If you mix diamonds with a rock it's less hard and you put them together, the resulting competence or resistance is not just some weighted combination of the constituents. In particular, we'll be modeling in this work here 2 types of hardness variables, which are the drop weight test and the bond work index. You see that, rigorously speaking, they are measures of competence or resistance to grinding, which is the process of breaking them down into smaller pieces. We'll also be covering this variable called metallurgical recovery in the locked cycle test, which is a variable that comes from the flotation stages. Empirical studies in the lab show that arithmetic averages fail as estimators of these variables, right? So if you go and you take one sample here with a given competence and another sample with a given competence here, and you try to use weighted combinations of these competence values, the lab experiments show that the competence of the mixtures never passing through this weighted combination, right? So we need to understand these challenges, and that's the slide that summarizes basically what we want to do. So the geometallurgical variables, they come from laboratory tests that are very time-consuming. They have a very small number of samples compared to ore grades, because ore grades are usually sampled, let's say, meter by meter along these drill holes. But these tests that measure competence and metallurgical recovery are very time-consuming and expensive, right? So if you look at the data set, for example, here, we have 2,000 samples of ore grades that have been composited. This data set is actually much larger, of hundreds of thousands, but we average them over intervals of 1 meter or 10 meters. But the laboratory tests that give us comminution indices are just 60, and the laboratory tests that give us metallurgical recovery are just 50. So let's say roughly 60 samples for the variables we want to model here. So we need custom mathematical models to predict these variables. We cannot rely on data-driven approaches. Gaussian processes rely usually on having data to not interpolate crazy surfaces, right? And we need to incorporate somehow some domain knowledge in order to constrain the types of predictions we will make. And this model should perform well under a small number of samples, right? So under small sample size. We propose the methodology that consists of 2 main steps, right? The first step, we will introduce a couple of Bayesian models that incorporate this domain knowledge for each of these geometallurgical variables. And they, as I said, they are ideal for a small number of samples because we are trying to constrain the predictions on this domain knowledge, right? You're not just using purely the data to make predictions. In the second stage, we will see how we can use this idea of Kriging and Hilbert spaces to interpolate this uncertainty to between drill holes, right? So we have 2 stages where we first make predictions along the drill holes, and then we'll do interpolation between drill holes with this idea of Kriging Hilbert spaces.
Do you have an idea of the number of words that you use that are not being defined? I mean, we are not specialists in this field.
Yes.
What do you expect? I worked in this field more or less.
Yeah, yeah.
Most people didn't. So
Yeah.
I think you should, Kriging, things like that. I mean, these are not trivial words. And
What terms, Charles, do you want to know?
All along, I mean, you know the things you did not know before coming into the field.
Yeah.
Bigly.
Yes, because we have a very broad audience. It's not just like people here in the room, but it's being transmitted on YouTube, right? So I'm trying to be as broad as possible to encompass people who have a more interest in understanding more of the mining challenges and the general picture of the problem. But I can definitely go with you later and go into more details on these terms. But I think,
at my age, I'm not the one concerned. And as I told you, I did work in this field.
yes, yes.
But, I mean, this submersion of, and it seems that you want to go to the end. No, you need people to understand. If we need 3 meetings to understand, we take 3 meetings. But the goal is
Yeah.
to finish us.
What I'll also do, Charles, that may help is that we have a paper already published. I'll share the preprint as well if something that needs more detail. I think that's not like the purpose of 1 hour talk. I think there's so much more to say that doesn't fit in 1 hour, right? So I think we can go after the presentation, go over the paper and discuss this in more detail. I think it's better for everyone, and then we can come back specifically with you to discuss this more. So just this overview of the methodologies that we have 2 tables which come from the comminution and flotation tests that we're going to create some Bayesian models that are specific to these variables. And then we're going to do this prediction along the drill holes, right? So each of these trajectories, we have Bayesian predictions or probabilistic predictions. Then, after these drill holes have predictions, we'll then perform some interpolation with this Kriging Hilbert spaces. At the end, the final result of the methodology is that each block of this grid model will have a full probability distribution for the 3 geometallurgical variables that we'll be modeling here, right? So before we jump into this methodology, let's just list here the R&D outcomes of this work. As I mentioned, we have a paper accepted in the Journal of Mathematical Geosciences. It's already in the process of edition, so it should come out in the following weeks, but the preprint is also online if you want to check it out. We have developed a software for the Valley team during this 4 months of work, right? So this software is shown here in the right, just a screenshot. It's a notebook where the team can play with the uncertainties in these sliders and customize the models for different deposits. And we also have published, along with the paper, an open data set to foster more geometallurgical modeling and research. At the process of developing this solution, we also made various contributions to open source projects that we also work actively on, like Geostats, Coda.gl, which is for compositional data, and table transforms. So the first part, as I mentioned, is introducing these Bayesian models, right? So we have to introduce Bayesian models for the 3 geometallurgical variables we listed. The basic settings here, because I'm thinking again of a general audience, it's not just people in mathematics, right? So think of the following type of prediction, right? We want to define Bayesian models for the 3 variables here, DWT, BWI, and LCT. Drop weight test, bond work index, these 2 are tests of hardness. And LCT, I'm just describing here the metallurgical recovery in the locked cycle test. These models will take as input a vector of explanatory variables, say chemical composition or mineralogical composition, and then we'll predict the distribution of the target variable in full, right? So given X, or some vector of explanatory features, it will try to predict the posterior distribution of these target variables. So the drop weight test, what is this variable? The drop weight test is a test that's performed in the lab where a standard weight of 5 kilograms is dropped over this small rock sample here. This small rock sample is then broken down into small particles, and these particles are fed into a sequence of sieves, right? So the result of this experiment is that if you drop this weight from 3 standard heights, height 1, 2, and 3, which have corresponding potential energy 1, 2, and 3, you'll be able to, for each of these energy levels, to describe the particle size distribution, right? So you have this rock sample break into small pieces, and then for each of these rock samples, you can measure this CDF of sizes. The industry then defines what's called the T10 values. What is this T10 value? So the idea is that whenever you increase the energy level, there will be a fraction of these particles with size smaller or equal than L over 10, where L is the original size. So you have a...
Can I just ask a quick question?
Yeah.
Is this size here, is it volume or is it...
Maybe just a length. It's just representative length, yeah. So you have like the original length L, and then you want to find the percentage of material that fits below L over 10 of the length, right, of the original length. This is defined as the T10th value for the if sample at the height h sub j, right? So given a height, I can define this number as the value of the CDF at L over 10.
What's the length of a piece like this?
It's very small. It's very small.
Yeah, but whatever. It's a diameter. How do you find?
So that's the question Roberto asks. It's like it's a representative length. It doesn't like import for the. It's not important for the specific purpose of the talk here, but it's just a representative length. You can measure it like in volume, but it's usually just a length that I can postpone.
It's a measure. It's a type of measure. It's not necessarily length.
It's an actual physical length, right? So you take a sample, you put into this machine. It has a length. It may be the diameter, the radius, or some representative length. Yeah, yeah. And then you measure these values of T10 for the 3 energy levels. And what the industry does is try to fit an exponential model for these 3 values, right? So you get the 3 values, and you try to find the A and the B in this exponential expression that fit these 3 numbers, right? So the idea of this Dwt Index, as defined in the industry, is the multiplication of A and B, and it measures the fragility of this rock sample. So there's studies in geomechanics which go outside of the scope of this discussion, but they have this representation of the index, which is just the multiplication of the coefficients in this exponential fit.
This might be a trivial question, but is there a reason why we would want to know the fragility of the...
So the idea is that you want to minimize the energy consumption in the plant. So the more fragile, the less energy you spend breaking it down into small pieces, right?
Are you obliged to break it down? I mean, can't you melt it, or
What is it?
are you obliged to break it down? Is it the only way to extract?
The idea is that you have to refine into smaller pieces to enter in flotation stages where this material can float with dynamic processes, right? So you have to break big pieces into small pieces to feed into flotation. So fluid will be carrying material with economic value to the top and material with low economic value to the bottom. So if the pieces are very large, they will just go to the top, to the bottom, right? So I think that's the idea. But I'm not the expert in this area, right? I'm the person that worked on the applied mathematics side. I'm not the mine engineer or the person that's in the process to answer this question properly, right? So this variable here, that's the product of the two, is the one that we want to model at the end, right? What happens is that this, as I mentioned, these parameters A and B, they come from this least squares problem, right? So they solve this least squares problem for their lab experiments. And so the idea is that you just express this objective function here for the 3 energy levels. So you say, I measure this at the lab, the 3 energy levels. I drop the height H1, H2, H3, and I measure this fraction of material. And these energy levels are standardized, so they're all fixed across all experiments. So you now want to find the A and B, which minimizes objective, and you can show that these expressions here hold as the solution, right? So you say the A is some expression in terms of the parameters that I mentioned, and is also a function of B, and there's an implicit equation for the value of B, right? The point here is that this is work by Lucas Rezende, is that if you have these expressions obtained with this industrial process, which is predefined, that's not our process, you can never find a set of any explanatory variables that makes a good estimator in terms of these explanatory variables linear, right? So you cannot find A in terms of a set of explanatory variables and B in terms of explanatory variables with linear models, right? So there is some nonlinearity that needs to be taken into account. In particular, we cannot use traditional geostatistical interpolation methods.
You mean jointly they cannot be linear, or each of them, none of them can be linear?
What matters here is that DWT itself is not linear, right? So that's what we are trying to model at the end. So the product cannot be linear, so that's what we're actually aiming for. So what is the idea here? So that will be a jump in the modeling, right? So you can go into the paper to find more details. But because, again, of limited time, we cannot go into too much detail here. The idea is that we will use the domain knowledge of this process to create a custom model, right? So the model is the following. We learned that there are 3 energy levels associated with the calculation of DWT, right? So we say that these energy levels at height J is going to be just increments of the energy level of the previous height. And this increments delta here will follow some given distribution, right? So we force this distribution to be some logit normal with some mean behavior. And then we say that this mean behavior here is a fine transformation of the explanatory variables, right? So we say something is a function of explanatory variables, and this is actually the increments, not the DWT variable. So the way this model works is that you sample these variables that are intermediate, and then you solve this least square problem at each sample. So you sample, solve a least squares problem, sample, solve a least squares problem, and then you can find the optimal A and B for each sample and define your DWT of the sample. Following this process, and by specifying some of these hyperparameters that control the prior uncertainty, we produce this prior distribution, right? So you have prior distribution for the energy level 1 of the fraction of material that is below L over 10, a prior for the second energy level, and a prior for the third level. You see that these vertical lines here, they're actual measurements from the laboratory, right? So you say, here we created a prior, and the measurements, they are within the prior, right? So that's prior check, right? Consequently, when we sample T10 like this, and we follow the same procedure that the industry follows, we have this prior distribution for the variable we want to model, the DWT, right? And so you have the actual measurements from the lab of DWT, and all we want to do here at this stage is to check that this prior measurements, this prior distribution includes all the prior measurements.
And do you believe that the industry has the right to methods? I mean, you don't question?
What is the question, Charles?
I mean, you're trying always to say the industry does that, the industry does that. But do they do the right stuff?
Yeah, there is values and processes in place that we cannot alter dramatically, right? So you have to go step by step in order to change the ways things are done, right? So this is just one need that the team had at the moment, and we had to model this DWT because that's what is used now to plan the activities in the mine, right? So we could also propose more radical changes, but that's probably going to be a next stage of project collaboration. And it's not going to be something that we can just go and say, do that way, that's different.
Long-term strategy.
Yeah. The second type of comminution index, which will be covered here, is this bond work index, right? So the bond work index, as the other index, it measures some resistance to grinding, right, in this laboratory mill. So here's just a toy illustration of what this grinding mill looks like. It basically is a container where you place this spherical balls, these balls of metal here inside of this tank. You put the samples inside and you start rotating, right? So by mechanical impact, you break the samples into smaller and smaller pieces because the balls of metal here have this purpose, right? There's empirical studies and laboratory studies that came up with this expression, which is called the bond work index formula. And there are many parameters that are involved in this expression, which again is subject to critic, but that's what is used, right? So that's one of the things that we had to take it for granted, right? So
you can imagine that if you shake, you might better the efficiency.
What is it?
If you shake the stuff, or if you take it and do like if you do with a bucket of water, then you can expect that it will be mixed better and perhaps either improve or lower the performance. But
yeah, I don't know. We don't have the ability to change their processes, right? So what we're doing here is just describing what's done. I don't know if they have other means of like doing this breakdown of samples, right? But that's just an illustration of what's behind the variable so that everyone has a context at least, right? So we cannot, first, we don't have the expertise to jump into too much detail here. And second, we want to model this variable because that's a demand from the team, right? So this is what is involved in the definition of this variable. There are two things that are just the center of attention here, which is these two values, P80 and F80. P80 and F80 are just apertures in micrometers, for which 80% of the material passes through. So you have a size of particles that enters into the experiment, and you measure the aperture for which 80% passes. And you have, after breaking down, after rotating this grinding mill, you have an aperture for which 80% of the material passes through. These two numbers are measured, and we use them as our second Bayesian model, right? So there are, again, many critiques that could be raised about this model, but the idea is that this is an initial work on how to handle these variables, right? So we have the F80 variable, which is this aperture at the entrance, at the feed, and we introduce this ratio here, G, which is the ratio between the product and the feed, right? So that's another random variable. And then we introduce a couple of other variables which are involved in that equation, the mobility, and there is the size of the mesh. There are many other things associated to the equipment. But the main message here is that some of these parameters, the mean behaviors, let's say, they're, again, a fine function of some explanatory variables, right? So you just say, here is a model. It's not, as any model, not correct. It's just a model that we tried to with this specific variable. And if you set the hyperparameters that are associated to location and spread, you get some prior distribution over these variables, right? So you have the prior distributions, again, plotted in these colors, and the vertical lines are the laboratory tests. The final variable that we want to model here is the locked cycle test, right? So the metallurgical recovery at the locked cycle test. The locked cycle test is a very complicated process with retroalimentation, right? So there is this material that's breaking down. It enters into this flotation stages, which is drawn here as this triangle shape, because material that has economic value goes one way, and the gang material or deleterious materials goes another way. And so you need to feed this material through a sequence of stages, which are just filtering out the material that has economic value from the one that doesn't. And then at the end, you have this final recovery, which is just the amount of, for example, the metallurgical recovery of copper is the amount of copper you get at the end from the initial mass of copper that you had, right? So given copper at the beginning, just a fraction of that copper can be extracted through these industrial processes. And so for now, we also do the same as we did with the bond work index. We simplify a lot of the physics, right? So we ignore this complicated dynamical system at this initial work and concentrate in one single stage, which is called the rougher cleaner stage, which is just a sequence of two of these boxes in the diagram. So if you focus on these two boxes here, that's, again, simple manipulation here. You have an initial amount of mass m that's fed into this diagram rougher. I don't know if that's correct pronunciation in English. But then you feed that into this rougher, and only a fraction of this mass is retrieved, which is this m sub r, with a fraction f sub r, which is the mass fraction of copper in the rougher stage. And this new mass is then fed into a second stage, which is also a mass of the cleaner, which is a fraction of mass in the cleaner times the mass of the rougher, right? So you're just filtering mass. And at the same time, in parallel to that, you have the ore grades that we have discussed before, right? So initially, you have a given mass. This mass has a given concentration of copper. And the idea is that at each stage, this concentration gets higher and higher, right? So you say the original ore grade of copper gets to an ore grade of copper after the rougher stage, and an ore grade of copper after the cleaner stage.
So you assume that there is no gold nor other fine material?
I'm giving copper as an example here because that's the main...
When you mine for copper, very often there are traces, at least, of gold, which completely change the
Yes, yes.
ore.
But the focus here was really copper. That was the goal of the work. Like, so they had a mine. They had gold as well, but that's the mine, the mineral that we are investigating in the entire work. We never touched predictions of gold here. It's just copper. And then after you have these variables defined, you can do simple manipulations to try to predict the metallurgical recovery of copper at the end, right? So just, again, simple algebraic manipulation, you say that the metallurgical recovery of copper after the two stages is defined as the mass of copper at the cleaner at the end divided by the mass of copper you inserted in the system, right? So if you just play the game of canceling fractions here, just inserting variables and deleting, you can express this metallurgical recovery after the two stages as this product of the ore grade of copper at the cleaner, the fraction of mass at the cleaner, and the mass fraction at the rougher. And here's the ore grade at the input, right? So this is just an expression or a relationship between the variables of the problem that you're constructing that's trying to extract domain knowledge from the problem, right? And now we want to model these variables in our Bayesian predictions, right? So one challenge with this expression is that it only works in open circuits, right? So we ignore completely the cycles that are more complicated and with retroalimentation and just consider these two stages in isolation, right? So that's not a good modeling approach, right? So we also notice that this rougher, in practice, the rougher stage is much more widely available than the cleaner, right? So you have data measurements from rougher much more easily than the cleaner. And so what happens is that we interrupt the process in the middle, right? So we go multiplying this fraction until we get to the rougher here, which is just ignoring some of the latest multiplications here. And from here to the end, we just introduce some affine transformation, right? So you say, I can predict until a certain stage with some multiplication of well-defined variables, which is just mass balance. And at some point, going forward, you just do a linear model. Because that's what we can do at this point. So we get this knowledge again, and then we introduce the random variables associated with the Bayesian model, right? So we say there is the metallurgical recovery that we want to predict. It's going to be some value in between 0 and 1. That's the logit normal restriction. And then we say that the mean behavior is going to be computed with this affine transformation, where this metallurgical recovery at the rougher, which is intermediate, is going to be the product of other variables. And this product of other variables will follow some distribution again, right? So it's just like trying to manipulate and incorporate the more and more variables from the domain as possible. And then if you look at the prior again, this is the prior distribution for all the variables involved in the model. And in particular, that's the metallurgical recovery, which is around 90% here for the prior, and the measurements from the lab, again, inside of the prior, right? After we specify the Bayesian models, we can then go ahead and do Bayesian inference to learn the posterior distribution, right? So we have the prior specification of models and the prior hyperparameters. We have the data from the comminution and flotation tests, which are these laboratory tests. And then we just perform a posterior approximation with this no U-turn sampler algorithm, which is the most widely, I think, algorithm nowadays in Bayesian modeling, that does this Markov chain to find out the posterior distribution, right? So you start with this blue specification of uncertainty, and then after performing this update, you learn the orange posterior distribution from the data. So with this, we then come to the point where we have Bayesian models with posterior distribution, so we have calibrated with the data. We can now perform predictions along the drill holes, right? So we say that given a new feature that has never been, let's say, used in the calibration, we want to make predictions of the posterior, right? So we say, what's the probability of my target variable given these features? We apply this for each cylinder along the drill holes, and then we can see that for each prediction, we get something like the following. For example, for this specific cylinder that I'm illustrating here, we predicted that the value of dWt has this orange distribution, the value of bwi has this orange distribution, and the value of the metallurgical recovery has this orange distribution. One particular thing that's important to highlight here is that you see that if you use the mean, right, this red curve here as your estimator, you'll always be far from the actual value measured in the lab, right? So we're just like highlighting here that these custom models, modeling uncertainty, give you the mode, let's say, as the best predictor, which is not necessarily the mean. We don't have this Gaussian symmetry, right? We don't have this usual assumptions about the variables, and that's why we say so much that it's important to quantify this uncertainty with domain knowledge in order to use something like the mode as the final estimator instead of just relying on the mean. An additional step, which is related to basically, I think, a bit of computational issue and a bit of representation, right, issues, we convert this PDF into histograms, and that's using intervals from the industry, right? So, for example, the drop weight test has levels of competence in the industry that have been standardized. So, from a value A to a value B, the rock is said, the mineral is said to have competence of type ETA, competence of type EXA, and so on. So we just break these intervals here. We perform the integration over these intervals and convert the PDF into a mass function, right? And that's, again, as I say, for two purposes. One is to have these objects that are much easier to handle in an algorithm, in a computer. We can just save this vector of numbers instead of thousands and thousands of samples from the Markov chain. And also because we will be using this representation for the next stage, which is the interpolation of histograms, right? So we'll be doing this as the second stage now. So far in this methodology, we say that we have predictions of the posterior distribution for these three metallurgical variables along the drill holes, right? So we calibrated with lab experiments, predicted along these drill holes, and now we have this full control of the prior uncertainty because the specialists can control the hyperparameters to specify the prior, right? The question now is, how do we actually predict this posterior distribution in between the holes, right? So we don't have data there that you can make the predictions. How to interpolate? And that's the second catch of the methodology, right? So we'll be using this idea of Kriging Hilbert spaces to interpolate PDFs or interpolate probability mass functions, right? So we want to interpolate this geospatial uncertainty for the 3D model. And this idea is very interesting. It's proposed by Alessandra Menafoglio in 2013. And the idea is the following, right? We consider that we have a collection of measurements that we have made predictions. These objects can be any vector in a Hilbert space. So it can be a scalar, a function, a PDF, or any object that lives in a Hilbert space. So you have ZS1 through ZSK, where S1 through SK are locations in space. And we assume, as I said, that they live in some Hilbert space. The idea of this framework of Kriging Hilbert space is that you want to define an estimator at a new location S, which is just a linear combination of these objects, right? So where this dot here is the scalar multiplication in this vector space, and this sum is this, and this addition is the addition of vectors as well. So for example, in this illustration here, say I want to predict functions at any given point of this domain, right? So I have a function that was measured at a specific location, another function, and I want to predict the function in between. That's what this framework is doing, right? So how we do this? Because you have a notion of inner product in this inner space, Hilbert space, you can define a norm, a distance, and consequently a notion of variance, right, to be minimized, right? So you can say, I want to find these weights in the linear combination which minimize this variance between my estimator and the actual value of this field, right? And you want to do this subject to this unbiasedness constraints, which is just saying, on average, this estimator will give this mean field. And this mean field here, in turn, is a linear combination of some polynomial terms, right? So you have this f sub L of S, which are polynomials in the coordinates. So you just define this. And these coefficients here, they also live in the Hilbert space. So you want to find the coefficients A sub L that measure this mean behavior, say. And you also want to minimize this variance, right? So if you are familiar with the traditional Kriging methodologies, we have just to do two simple generalizations to get this thing working, right? The first is that we have to model this mean behavior with some sort of generalized squares that supports Hilbert spaces, right? So we want to find the coefficients A hat that approximate that mean behavior, and that is like a vector Z of objects. So you have this vector Z with functions or with PDFs or any objects, and you want to take a linear combination of these objects, which is given by this expression where F are the polynomial terms and sigma are just some covariance that's specified. And the second generalization to make it work is that you have to express your covariance model in terms of norms, right? So usually when you measure covariances between scalars, you just take the square difference and you do this empirical estimate. Here, just replace the square difference by the norm, right? So you just use the norm in the Hilbert space to subtract the functions and make this estimate of the correlation function at any distance h. Now it's the second idea which connects to the idea of Hilbert space or complements it, which is the idea of compositional data, right? So we're saying that we can interpolate objects in a Hilbert space, which are any vectors with inner product and so on and so forth. What vectors are of interest for this specific application, right? So we have predicted probability distributions at the drill holes, right? So we want to interpolate probability distributions. So we have this idea by Eigen in 1986, which is this branch of statistics called compositional data analysis, which is a specific space that was developed for variables or vector variables with constraints, right? So you say, if I have a vector variable P, where each of the entries of the variables are never negative and they're sum up to some constant, for example, probability distributions, histograms, he developed this vector space called the Eigen space, which has the structure of a Hilbert space, right? So you can say, you can define the scalar product with this vector, which is defined by this, and the vector addition, which is defined by this, where this closure here is it's called the closure operator, which is just normalizing the results of these operations here. And you can show that these two operations with this definition of vector variables form a Hilbert space. So putting the two together, we have the scalar multiplication and vector addition defining the vector space, plus a definition of inner product here, which is a definition of inner product between these histograms, which is also defined in this literature of compositional data analysis. As you see, it just takes into account relative information, right? So you're just looking at fractions in log scale. You define this space of PDFs where you can just take linear combinations and morph one PDF into another. So for example, at the top left here, we have a PDF P, and at the bottom right, we have a PDF Q. If you take lambda in between 0 and 1, you can morph P to Q, right? Gradually morphing the shape of the PDF. And so that's what we'll be using to interpolate PDFs between drill holes. So putting it all together, we have predicted PMFs or probability mass functions at the drill holes, and we have now ways of interpolating these PDFs in between for any location, right? So what is the net result of this modeling approach is that we can, at each block now, make a prediction which is a full PDF of the variable of interest, right? So P here can be, for example, the posterior probability of DWT or the posterior probability of BWI and so on. And with that, we can do some post-processing to highlight some important features for planning, right? So I can, for example, take some measure of uncertainty, for example, the entropy of this posterior for each block, and create a map, let's say, of uncertainty, right? So this information can be useful to decide, okay, this region here is more uncertain than another region. You can also take any statistic of interest, for example, the mode. As we saw, the mode may be a better estimator than the mean value. And we can do this for any of these geometallurgical variables that we have come across and have modeled, right? So A side note is that this full methodology avoids the traditional path of doing geostatistical simulation, which is Gaussian simulation. And because of that, it's very fast to run, right? So we don't do the traditional geostatistical simulation. We go through this path of predicting with Bayesian models along drill holes and interpolating with Kriging. And we still have full uncertainty, let's say full probability distribution at each block, but without simulation. And this gives us models that are generated in 6 minutes, for example, in a desktop. There are some important remarks and many more details in the preprint, right? So I'll just highlight some of them here that are more, let's say, general for the general public. We've made as pros, right, probabilistic predictions that are constructed from domain expertise, which I think is the biggest value, right? We work together with the value team to extract this kind of knowledge and try to customize the model as much as possible. And we have these fast updates of uncertainty, right? Because we don't have to generate hundreds of these 3D models to take empirical estimates from these realizations. We can just skip this part and do the modeling of the posterior uncertainty directly. On the other hand, there are some challenges, and we discuss them in much more detail in the paper, which is, for example, how to interpret these variograms of probability functions, right? So at some point, we have to estimate some correlation function of probability mass functions. That's very hard to interpret as it's usually done in the industry. You look at variograms that look very different than usual. We also have oversimplified the physics for some of the variables, specifically BWI and LCT, because these are very complicated dynamical processes that deserve a full project on their own, right? So we don't have enough time to cover this into full detail. These are worth investigating in a project on its own. And there are other small details that we discuss in the paper, like binning choices to convert PMFs to PDF to PMFs and so on. The conclusions here are that we addressed this problem of interpolating geometallurgical variables with this combination of Bayesian modeling and Hilbert Kriging. And we applied the methodology to a real copper deposit, right? So that's actually real data, it's not synthetic data. And this data is published as a company material in our paper. We consider these 3 variables that we mentioned during the presentation, and we just visualize the posterior distribution and seeing that the shape that we model is preserved in the interpolation, right? So any point you predict, you see that skew distribution, which is typical from these variables. We will not be centering or making things Gaussian without intention, right?
You did only green, or you did also brown?
This one had how many drill holes? I don't remember out of my head now because I'm already touching another data set, but I can double check that, Charles. I don't remember how many drill holes because the question of green or brown is
about quality.
Is about how mature, right? Like you are. Is that the question you were asking?
No, the question the brown. I mean, the green stuff is where you know there are a lot of power of quality, and you're just trying to get to the best one. But
yeah, it's usually a function of the number of it's connected or at least correlated to the number of drill holes. I don't remember off my head how many, but this is a very well developed mine deposit. It's not something that they just started. They have been working on this for. I cannot say in public. I can say afterwards if we need more information that's sensitive. I cannot say on YouTube right now. And so all these probabilistic predictions, they presented satisfactory geospatial continuity, right? So we have seen these maps of entropy, modes, and stuff, and you see that there's at least some continuity spatially, which is important. We cannot predict something that's completely random. And then we just emphasize that more experiments are needed with different data sets to assess the methodology, to find problems and issues that are specific with any of the modeling stages we made. As I mentioned, there are additional resources for those who are interested in getting more and more details, right? So if you scan this QR code, you go to the preprint, which is already online. And if you are interested in geospatial problems, I'm happy to share. Just connect and talk to me. With that, I would like to open for questions.
So, yeah, we might have a few questions in Pigeonhole, but we're certainly happy to have questions also from our physical audience.
Thank you, Julio, for a very nice talk. So I have one question. So you commented in the beginning that the parameters that you are interested in are linear, are not non-linear, yes, in some sense. But the last model that you showed, Hilbert Kriging, as far as I understand, it's linear. Yes.
Good
so how does it
Awesome.
affect the?
Awesome question, Julio. That's awesome.
Okay.
So the idea here is that we are not interpolating the variable directly. We're interpolating the shape of the PDF, right? So it's like a wavy explanation to say we're not directly modeling the variable. We're modeling the uncertainty of the variable and interpolating the uncertainty, right? So we're saying, here is a PDF. I know that the variable itself is not linear on the explanatory variables, but I can assume, let's say, with more flexibility or more loosely, that at least the shape will be morphing linearly. That's the assumption. That's a big assumption, of course, but we're interpolating the PDF shape and not the values, right? That's the point.
But the mean, yes, so if you have some means, yes, and you interpolate linearly, the mean will be also some arithmetic mean, and this
Yeah,
is...
so you make linear coefficients on the Hilbert space, but they don't necessarily translate into linear in the variables, right? Because the inner product, for example, is the summation of the log ratios of these entries of the vector. So there's some linearity. Let me show the expression here again.
So it's for the choice of your Hilbert space, yes, where some nonlinearity is hidden.
Yes, basically like we are using this. So these linear combinations in PDFs don't translate in linear combinations of the variable, right?
I see. Okay, thank you.
So I actually have a question regarding that. Of course, Eichenson's work is fairly well established, right? But for the benefit of those of us who haven't worked with it before, do you have any intuition as to why that would be the right geometry somehow on PMFs?
Not at all. That's
okay.
the idea that I think is one of the main limitations, Roberto. I think we've made this step of going through modeling that way, but intuition is, for example, the intuition of the correlation function on the space, how to interpret this. Like, usually when you model the variables directly, like OR grades, we can interpret physically. We say, oh, the correlation range corresponds at this physical size of the geobody in the subsurface. The height corresponds to the variance of the variable you're measuring. But when you go to this more exotic space, we lose a lot of this intuition. And I think, answering your question very honestly, I don't think we have a full understanding of what's the implication of using this interpolation of shapes.
Right. Okay. Thanks. More questions? So, yeah, I have a couple more questions. If you have a question?
Thanks, Julio. So, as far as I can tell, the results you're showing are all in training data. Do you have any results on test data or on unseen data?
So the predictions that we make on the space, right, the interpolation, we don't have data there, right? So we calibrate the models along the drill holes, and then we make predictions on in between, right? So one thing that we want to do as the next step is validating this matter, right? Assessing with a different separate data set where we do the interpolation, but not in a region where we had drill holes, but in a completely separate region spatially, right? So we have these drill holes here, we calibrate, and then we interpolate. But what about if we calibrate here and predict there, right? So that's one of the things we didn't try because of time constraints. So answering your question, we concentrate on the same physical domain. Spatially, it's like just the same box where you're doing all the work.
But I mean, so do you have a measure of error? So you make your model, you make a prediction, then you have a data point you haven't used at all, and then you compare your predictions to that. Do you have that?
Yeah, no, so that's one of the things. Because in order to make predictions, so there's one thing that I didn't mention here, that let me come back here to this point, which is very important, is that in order to assess, where's the picture? In order to assess the final result, let me show here, here. In order to assess the final result at the scale of the block, which is usually 10 by 10 by 10 meters, we make the prediction there, but there is a change of support, which is something from the geostatistics, which you have measurements at cylinders, which are points basically, and you scale the variance to match the block scale. But in order to assess the validity of this result, we need to have measurements at block scale. But in order to have measurements at block scale, the industry will need to go in the field and have estimates for the whole block, which are not available, right? So we only have measurements at cylinders, which are very small. We'd have to make predictions and have a base case that's block scale, and that's not available.
I see. And then, so out of curiosity, when you say, so how do you validate your current modeling assumptions, let's say? So you have a bunch of things that are either Gaussian or almost Gaussian, right? Mm-hmm. Which is something you started saying that might not be great.
Yeah, hierarchically, they are like each component is Gaussian, but putting together becomes something not, yeah.
My point is like, how do you know Gaussian is sort of a good assumption on your model?
Yeah, that's a good question. So basically, like what we did here is like follow the most simple path possible without, like being what you don't want. So we just take that each components are Gaussian by simplicity, and then we combine them into non-trivial ways. So that's the simplest possible approach.
Right. More questions from the audience? Otherwise, I have one additional question, perhaps, which, I mean, besides the Gaussian assumption on the prior, right? The Gaussian, as you said, a hierarchical model with Gaussian priors at each stage. You also have these hyperparameters, right? Mm-hmm. How did you fit those, and is the model somehow too sensitive or not at all sensitive to these choices?
Good question about that. So some of the hyperparameters, let me give an example here. I think the first one is a good one. This one. So let's see one more. No, it's here.
Well, there are hyperparameters
yeah,
over there.
There, yeah. So some of these hyperparameters, like delta here, which are measures of location, right? So where the center is. We just relied, let's say, on a value that is typical for these types of variables in the industry. They are physical variables. They have been working on the field for a while. They say, let's say, this is a representative guy for this value, right? Because these parameters are usually associated with the location or spread. And this spread, we leave it open for the modeler. So the person that's using the tool, he can control the prior with a slider and just open up or close it up as a function of the deposit that they're investigating. So the location, we try to somehow give a good first guess, but allow also them to change. And the spread is completely open. We just open it as much as possible in the physical range that we thought it's a good physical range.
Right, but I mean, surely when you use your slider, right? The priors are going to change, and the posteriors also.
Yeah.
How big a difference is it? Is it too drastic,
prediction.
the change when you move change the parameter a little bit?
That's a good. So the predictions become very visibly more shrinked or more open, right? So that you control the uncertainty. That's the expected result. But sensitivity in terms of how, for example, the prior influences the predictions should be assessed if we had the actual ground truth, which is at the block scale, right? So we didn't had a way of measuring how far we are from the truth, right? We could try more experiments on that direction, but we didn't do. So basically, it's something for future work, I guess.
All right. Do we have more questions? Are there any questions on Pigeonhole that you want to answer? Or?
Yep. Let's see here. There was.
Well, I should also check YouTube because sometimes people ask questions on that.
I don't know if YouTube is open. So it's saying, is the methodology adequate for other types of mineral deposits? If not, what would need to change? So the idea is that, as I mentioned, like you can customize your prior uncertainty depending on the deposit, right? So because this is not, let's say, a fully automatic methodology, right? We let users and humans to interact with sliders and play with the different parameters. If someone is working on a specific deposit, they can control the prior uncertainty, the locations, and then adjust this for different deposits. We didn't assume anything about being copper here, but we didn't also try any other deposit. So it's open. We need to assess it with different mineral deposits, I say.
Thank you. Well, there don't seem to be any more questions, so let's thank our speaker. Oh, you have a question.
Yeah, I have one question. Many, but just one for now.
Do you mind holding the microphone?
Yeah, okay. So you mentioned some way of getting data, but some in the mining industry, at least sometimes has ways to get data, for instance, by planes, and these data are sometimes extremely rich.
Yes.
So how much of, but this does not correspond to an actual mine, or does it?
It's a real mine.
So you could compare what you get from one type of acquisition of data to what you would get if you add other acquisition.
Yeah, that would be a path, definitely, like considering remote sensing as some extra information to get information at larger block support in order to...
Also. I mean, anything, all the things which are being used.
Yeah.
Like
the challenge is actually we need to map these measurements to the actual variables we're discussing here, right? Because there's remote sensing, they don't measure, for example, the competence of rock directly, which are only measured in laboratory tests with mechanical impact, right? So you could try to find a relationship between remote sensing measurements to the variables and then use that to assess, but that's an extra step right? It's not guaranteed that it's going to be like any better than just trying to do estimates of this block support in a different way without extra information.
Thank you, Sean. Okay, so maybe now we don't have any more questions from the audience.
No, we have question. We just
Oh, no,
go
okay,
back.
for maybe, okay. Questions that should be asked during the talk, I mean. But, and assuming that's the case, so yeah, let's thank our speaker again.
Thank you.